Okay, hello everyone. We're gonna talk about score functions now. Everyone's favorite topic, I know. Score functions are important because score functions are effectively how score functions are a type of way that we do estimation, and they're a particularly good estimation function. So we're just gonna get started. The same old notation that we're used to, x1 through xn, IID, normal, some distribution f, and then there's some parameter here, mu, right? And mu can be anywhere in the real line. This is the whole parameter space. Okay, and since they're independent, right? This is the ID, this is the independent, and this is the identically distributed. Identically distributed means they all come from the same model, same thing, and independent means they're, of course, probabilistically independent. So their likelihood function, because they're independent and they're identically distributed, is equal to this thing. And I'm going to take the log of this because it's just easier to deal, maximizing the log. It's easier to deal with this. So I take the log of L, I get little l right below it, right here. That is the log likelihood function. And of course, the product turns into a summation sign, and I get the sum of log fxi's. All right. The score function is actually just the derivative of the log likelihood. That's it. I'm going to take the derivative of that thing. So what does that look like? Well, let's do it but let's do it without the summation, okay? Just for one observation, 1xi. And I'm going to call S is for score function. So we know what we have here, okay? And so S here is the score function. And you take the derivative of the log likelihood with respect to theta. And so I've just replaced in what the log likelihood is, all right? And the derivative of the log of x is, of course, 1 over x. And if x is a function, here's you have your 1 over x part. And then you got to follow the chain rule to get this next piece. So this is going to be an important form that we use and that we see later on. Now, for multiple observations, because I'm taking the derivative of the sum, I'll just get the sum of the derivatives. So here, in this piece down here, I have the score function for all the observations, all n observations, is the sum of the individual score functions. Okay, which you can just write out like this. Is pretty straightforward. No big deal. All righty. Let's do the next page. Now, there's some important pieces here, some very useful things that I think are going to be helpful. First is, in order to get the maximum likelihood estimator, we're going to take the score function, we're going to plug in the data, and we're going to set it equal to 0. Now, whatever parameter value happens to make this thing equal to 0 is going to be the maximum likelihood estimator. That's by definition what the maximum likelihood estimator is, that thing. Okay? Now, the reason that's important is because the way we find the maximum likelihood estimator is we're setting the score function equal to 0, right? So to find the maximum likelihood, set the score function equal to 0. Well, this only makes sense if, in fact, the score function is 0. And this is going to turn out to be the case. So it turns out the score function is an unbiased estimator of 0, meaning on average, the observed score function is 0, even if you spell it correctly. So that's what this says. This says the expected value of the score, that's the score function. The expected value is this outside piece here. The expected value of that thing is 0. And this turns out to be an important property, and it's important, and I'm going to just quickly prove it. It's important because of the conditions under which it is 0. Notice here, you can already tell, I'll put it in blue. Notice here, this theta here and this theta here are the same theta. So essentially, you're taking the expected value under the true observations. So the way to think about this is, well, let's just do the proof. The proof just turns out to be pretty straightforward if you start with a little trick. We know that densities integrate to 1. So I'm going to start there. I'm going to take the derivative of both sides. Now, the derivative of 1 is 0. Well, okay, that's fine. Now, what I'm going to do is I'm going to take this derivative and I'm going to exchange the order with the integral. And this is okay as long as the limits of the integral don't depend on theta. We can't have that. Okay, so now I have here, and I have the derivative with respect to f. So what I'm going to do is I'm going to multiply by 1. Multiplying by 1. I'm going to rewrite things, and notice that this part here, look like the derivative of the log, because the partial of log f of x theta partial theta is equal to 1 over f times the derivative of f with respect to theta. So that's what I have here in red. Then what's left over in this last piece here is in purple. And of course, this looks like an expectation, right? That's an expectation. So the expected value of a function of g of x is equal to the integral of g of x, f of x, dx. That's exactly what we have here, except this g of x is this part here, is this derivative here. Right? So this is the integral, the expected value of the score function, which we can write like this. The key part here is that notice that the integral is taken, I'm going to use a light green here. The expected value is over the true density, but this true density is also in the score function. So you're using the same density twice. So the score function usually comes from what we call the working model. And if the working model is equal to the true model, then the expected value of the score will be 0. And that's when maximum likelihood estimator is good. So that's basically how it works. And that's the important piece, that doing maximum likelihood means setting the score function to 0. And setting the score function to 0 makes sense when it's 0 on average, because you'll be doing the right thing on average. All right. Notice that we switched the integral and the derivative. This switch is allowed when the limits of integration are free of theta, and we'll come out to this later. This is commonly referred to as a regularity condition. And then again here, notice that the expectation is taken with respect to the true value of theta. Okay, otherwise the score function is not necessarily unbiased. What I'm going to do now is I'm going to just write some other notation so we get used to looking at this. Suppose I take my score function. This was the thing that I just called SI before. I'm just going to call it Y, something else. Then we have the expected value of Y is 0 under theta. Well, we know that sample averages converge to their expectation, right? In this case is 0. So we know that this sample average will converge to 0, and this is by the law of large numbers. Okay. And let's see how this works in practice. Let's take a look at an example. I'm going to look at Poisson data. Here's the density of the Poisson distribution. I'm going to take the log density, right? This guy is equal to log of f of x lambda. So I just get the log of that here. And then this is for one observation, right? This is for one observation. This is for all the observations, right? Remember, just like the likelihood for lambda given all the data, here is going to be the product of the f's x lambda, right? On the log scale turns out to be the sum. So all I did was I passed the summation through here, and I get this. And now what I need to do is I need to take the derivative of that thing with respect to lambda. So the derivative of the first term goes away. The derivative of log lambda here times the sum of the x gives that term, and then this gives that term, and this just goes away. So I'm taking the derivative with respect to lambda, and there's no lambda there, it's a constant. Okay, well, so then I have the sum of the xi's over lambda minus n is equal to 0. So the sum of the xi's is equal to n times lambda, and then the sum of the xi's over n is equal to lambda. So this implies that lambda hat is equal to x bar. This is the MLE, which is what we have right here. These are things that we've done before. It's good to see them again. And it's pretty straightforward. So finding the maximum likelihood estimate, don't forget, we're doing the same thing as here's the likelihood function, right? Here is this is lambda. This is lambda hat or x bar, right? This is where the likelihood function is the max. And its slope is 0. So that's what we're doing. We're finding where the slope is 0, right? These are all things that should be making sense now as things come together. All right. Notice that this is a random variable based on n observations, so I can take its average. And actually, I don't even need to take its average in this case. So the expected value of the average is equal to 1 over n comes out. Just don't forget the score function was the sum of the xi's over lambda minus n. That's s. I took the expected value of that sucker. Right? So I take the expected value of that. And so that is equal to the expected value of the sum of the xi's over lambda minus n, which is the sum of the expected value of xi over lambda minus n, right? Which is n lambda over lambda minus n, which is 0. That's all what's here. Again, the important detail, the subtle detail is in calculating this piece right here, right? I calculated the expected value of this thing, assuming that the x's were Poisson. But this is also our working model. That says working model, even though it doesn't look like it. All right. So this happens only if that happens. That means the score function is 0 on average. The score function is 0 on average only if the true model and the working model are the same thing. The score function is 0 on average only if the true model and the score and the working model are the same thing. The working model being the model that is in your S. True model being the model that you compute the expectation over. You should say this a couple times, get used to it, get comfortable. It will come up in a couple cases. All right, let's take a look at some general properties here. I have x1 through xn is some general distribution theta, some parameter space. The score function is the first derivative of the log likelihood. Now, we know that the average score function converges to 0 by the law of large numbers because the average score function converges to its expected value, which is we know is 0. And we know it's 0 because the true model equals the working model. It's because X is distributed F. We're going to change that up in a few classes from now, but for now, this is going to stay the same. All right. Well, this is a random variable here. It's a sample average. I might also want to know what's the variance of that thing. So it's helpful to calculate the variance here of the average. The 1 over n comes out squared, right? Things come out of the variance, they get squared. And then, of course, I have the sum of the variances minus the sums over the covariances. This goes away if things are independent, right? This is standard variance type calculations. And then the sum of the variances, I have n of them. So I end up with n, and that n cancels with the square. So I get the variance of S over n. It looks just like a normal distribution where if you had a mean, the variance of that thing, well, hold on, go away. The variance of the mean is equal to sigma squared over n. So this is the same idea. What's going to come out, what's going to happen is that the variance eventually of the score function is going to turn out to be an important thing. So let's take a look on the next page. Let's just compute some of these things and get used to computing them. So I can apply the central limit theorem, which is, remember that for the normal distribution, the central limit theorem says x bar minus mu over sigma times the square root of n, that thing is normal 0, 1. And it's approximately normal by the central limit theorem, right? Well, if mu is 0, then root n x bar is approximately normal 0 sigma squared, because I just brought that guy over here. And that's what I get here. So I get this thing, which is, this is the S bar minus 0 times root n, which is just this, goes to be normal 0 with whatever the variance is. Just leaving it as the variance. I don't know what it is. I could give it a symbol, but I'm not so up for symbols at the moment. All right. Or I could standardize by the variance. This is the exact same statement as up here. It's just, where do I want to put the variance? Do I want to put the variance in the limit, or do I want to scale by the variance at the beginning, right? So that's kind of what I've done. Now, when S is exactly normal, so if the data are normal, then I don't need the central limit theorem. This is all exact. So let's suppose I take the actual x's, normal mu sigma squared. I'm going to treat sigma squared as known. Here's the log density, right? This is the log density, right? Because the density is 1 over the square root of 2 pi sigma squared e to the minus 1 over 2 sigma squared x minus mu squared. If I take the log of that, I get this thing here. All right. And then if I take the derivative of this thing with respect to, so I want to do partial mu of this thing. So if I do that, then that part's going to go away. And then I just have to take the derivative with respect to mu of this piece here. So the 2 will come down, and then I have to do the chain rule. I'll get the minus 1 on the inside. The 2's cancel, and I get right here. I get x minus mu over sigma squared. That is the score function for a normal distribution. And I can just calculate what is the distribution of this thing. So the distribution of this thing turns out to be normal 0, 1 over sigma squared, just by properties of means and averages. And so the expected value, of course, the score function is 0. And then we know that the variance of SI of the score function is 1 over sigma squared. The important thing here is to look at, we have this interesting thing where the variance of the score function is equal to 1 over the variance of an observation. So the variance of the score function and the variance of the observation are inversely related. Variance of the score inversely, however you write inversely. Oh man, that is terrible. So here, let's just get rid of the variance of the score function is inversely proportional to the variance of an observation. And this will be helpful for understanding behavior later on. This little relationship is helpful. That means if you have big variance, right? Big variance, then you have the score function has small variance. If you have big observational variance, if you have small observational variance, you got big variance of the score function. So these are just some more things here. I am just look at the sample mean by itself, of course. And this is another central limit theorem, so no asymptotics needed. Okay, you should be able to write these down and these down simply by using properties of expectations and variances. All right. The last piece here, well, let's do an example before we do the last piece. Let's suppose the data are F, and I'm leaving all this the same, and we know that the score function's unbiased, but what do we know about the variance of SI? Well, the variance of SI I can write as the expected value of the score function squared minus the expected score function whole thing squared. But this thing is going to be 0 because of that. So you get left with just this and this. And this guy, whoops, here. Well, I don't want to write over that. So this guy turns out to be an important quantity, which I'll define on the next page. Let's do a quick example, just so that we get comfortable with what that is. Here's the score function S that we calculated for the Poisson distribution, remember, for one observation. I'm going to square that sucker. So this is just completing the square. And then I'm going to take the expected value of SI squared right here. That expected value gets pulled through. I know that this is lambda. And I know, what is that? Well, I know that the variance of xi is equal to the expected value of x squared minus the expected value of x quantity squared. And for a Poisson distribution, I know that the variance is lambda, and this will be lambda squared. So this has to be that the expected value of x squared is equal to lambda plus lambda squared. Okay, so these lambdas cancel, and I get 2. And then here, this part is right in the top here. And then I reduce everything, and I get 1 over lambda for the expected value of s squared, which is the variance of SI. So it's 1 over the regular Poisson variance, 1 over lambda. Okay, so that should be pretty traditional. So here you go, pretty traditional. That should be pretty, look familiar. So here the variance of the score function is 1 over the variance of x. And the variance of the sum of the score functions is n over lambda. And of course, the variance of the average score function is just this. So I get 1 over n squared, n lambda, 1 over n lambda. Again, these are things we should be comfortable doing in some practice. So this is the important parts here. And then I'm just going to give you some names here, some definitional names. So it turns out that the variance of the score function is an important thing, and we call it the Fisher information. We call it information. And it measures how much information is in the sample. And so notice that I used the regular I here to be the variance of the score function. I used I with the subscript of n to indicate the information in a sample of size n. And if they're independent, it should be n times the information in an individual. And what we want in many problems is we want the information to go off to infinity. And this happens in most regular problems. This is going to be closely related to things like called the Hessian matrix and various things when you're doing numerical computation, and we'll get to that in the very next lecture. So Fisher's information is actually called the expected information. So it's possible to estimate the information itself by just computing the minus log f theta squared, square it, sum them up, and divide by n. So you can do this empirically, which is not a problem. And so here, this empirical estimate is not the expected Fisher information. It's an estimate. So we usually say it's V hat. The expected information is this guy, partial log f partial theta. I'm leaving out that part here. Squared. It's the expected value of that thing squared. That is the Fisher information. What you have here is an estimate of that thing. It's important to keep the two separate, and we will deal with these more as we go away, and we learn these various quantities. All right, thank you.